Hi, hello, my name is Logan. So we are doing the system 1. So this how first we have to find the poles and the zeros. So now the transfer function given as k is constant and poles is s plus 5, s plus 8, s plus 10. So you transfer it, so you get like s cube plus 23s square plus 170s plus 400. From there you find the poles, which is negative 5, negative 8 and negative 10. So then after this we find a breakaway point. The formula is kgh equals to negative 1. So this is the breakaway point, and after that let sigma to the angle. So this is the dk over the angle to find it. Then after this we find what is the breakaway point, which is negative 6.214. Then after that we can proceed to the next part, which is imaginary axis. So this is called ds equals to the transfer function. So this we using the Root-Horowitz criterion. Condition for a row 0 helps determine k. Equals to 3510. Okay. Then we can plot the graph, the board plot. So this is our board plot. After we done our board plot, we can identify that the overdam, which is the range k is more than 0 and less than 8.209, and critically damped, which is negative 8.209, and undammed and underdamped. So the dominant pole from the root locus, which is 4.2 and 5.8, which is j, okay, yes. So then we can find time peak and time peak to crest. So yeah, here this is the time peak and time peak crest. Okay. So this is what it is, and then let's go to this part, which is root locus and the step response. So this is our dominant pole, and this is our overdam, and this is our critically damped, and this is our undamped. So the undamped for the output response is like so noisy with this kind of graph, and this is our underdamped. Okay, that means like it is like undamped is like unstable, which is so that it is unstable. Yes, so this is our discussion part for system 1. So this is our system part, and that's all. Thank you.
So for question K, in order to design a lag compensator, so first we calculate the phase margin by using the given value, damping ratio 0.25. Then we get this board diagram, and then we calculate our new gain K, which is K, and using formula Kp, then we replace a new K into our system 1 transfer function. Then we get this board diagram. Okay, by using a formula negative 180 degree plus our new desired phase margin to get this value 152 degree, and based on this degree refer to the phase plot, we will get the frequency, and magnitude plot will get our magnitude. Based on these two value, then we calculate the value for the 1 over t, 1 over alpha, 1 over alpha t, then sub into the formula, then get the new lag compensator transfer function, and this is our lag compensator board diagram.
My name is Tnioh. For the system 2, we get the transfer function k times s plus 0.5 over s plus 1 times s plus 3 times s squared plus 7s plus 5. Then we transfer it, make it simplified, and then we can get the pole and the zero for this transfer function. And the b is the breakaway point. We get the formula kgh equal to minus 1 and k equal to minus s power 4 plus 11s cubed plus 36s squared plus 41s plus 15 and over s squared plus 0.5s. And we replace s to the real variable, which is the sigma, and the substitute in. After that we divide and differentiate the dk over d sigma, we get the 2 sigma power of 5 plus 12.5 sigma power of 4 plus 11 sigma cube minus 23 sigma square minus 30 sigma minus 7.5, and so we get the root, which is the sigma equal to negative 0.3597, negative 0.8842, negative 4.6935, 1.436, and negative 1.7491. For the C, the j omega axis crossing point, in this case we know crossing point, and for the D, the angle of asymptote, and so we, by using the formula, when the k equal to 0, the angle is 90 degree, and the k equal to 1, the angle is 270 degree, and k equal to 2, angle is 415 degree, which is the null exit. And for the real exit sigma a, by using the formula and use the negative 1, negative minus 3 minus 0.8074 minus 6.195 minus and 0.5 and over 4 minus 2, then we get the real exit is the negative 5.2502. For the F is the damping ratio. We use the overshoot 10% and substitute the damping ratio formula, which is the damping ratio equal to negative ln 0.1 over square root 5 square plus ln square times 0.1. Then we get the damping ratio is 0.5911, and the damping angle is equal to 53.76 degree. So we get the dominant pole is 5.2 plus minus J7 with the angle 53.76 degree. And the time, peak time is, by using the formula, is equal to 0.449 second, and the compensated time is equal to 0.2993 second, and the omega DC is equal to 10.5, and the DC gain is equal to 7.7, and so we get the compensated nominal pole is S equal to 7.7 plus minus J 10.5. Uh, we know that the contribution of angle between all zero and pole are compensated dominant pole, which equal to negative 180 degrees. So after calculate this all, and we can get the transfer function for the PD controller is the S plus 27.95 degree, and the GPD SGS is equal to K S times S plus 0.5 times S plus 27.95 degree over S plus 1 times S plus 7 times S squared plus 7S plus 5. And we choose the ideal integral to be the GPI as equal to S plus 0.5 over S. Then by comparing the GPID, so we get the GPID SGS equal to K times S plus 0.5 times S plus 0.5 times 5 plus 27.95 degree over S plus 1 times S plus 3 times S squared plus 7S plus 5. And so after calculating, we get the KP equal to 1410, KI equal to 349.375, and the KD equal to 50. We keep the coding S equal to TF bracket s to define the Laplace variable s, and the k is equal to 50, which is the gain, and we key in the transfer function g equal to k times s plus 0.5 over s plus 1 times s plus 3 times s squared plus 7s plus 5. And then we type for both bracket g, which to generate the both plot, and the margin g, which to display the phase margin and the gain margin, and the grid on to add grid line for better analysis. And this is our plot diagram. We get the phase margin to 93.9 degree at the 5.22 radian per second, and you can see the for the gain margin, this is the frequency, and the magnitude is at the negative 0.0309, and this is the phase margin, and get the value there.
My name is Tnioh. So now I will present the system tree. So the system tree is given is k s plus 2 over s plus 5 s squared plus 7s plus 12. Then we find the pole and 0. The pole is negative 5, negative 3, negative 4. Then the 0 is negative 2. So part B, we'll find the breakaway point. After that, after using the formula, then we found that the breakaway point is negative 4.532. Then before we draw the rule locus, we need to find the angle of asymptote. So we substitute k equals to 0, 1, 2 into the equation. Then we'll find out the different angle. Then the angle of asymptote is 90 and 270. So the 451 is rejected because it's not in the range. Then part C is we use the Roof-Worth formula to find the k. So the k is 504. Then for the even polynomial, we found out that is s equals to plus minus j 6.856. Then part E is to find the overdamp, critically damped, underdamped, and undamped. So after that, substitute into the formula, given s equals to negative 4.532, then we found that the overdamp is 0.1506. The critically damped is k equals to 0.1506. Undamped is k equals to 504. Underdamped is between 0.1506 and 504. Then this is the rule locus. Then on the part F, to design the PID controller, then for 10% setting 10% setting time, then we use the formula to find the compensated dominant pole first, which is s equals to negative 7.476 plus minus j 10.2. Then we find the angle, which is the first angle is 103.64. Second angle is 113.69. Third angle is 108.82. The fourth angle is 118.23. Then we substitute into the formula. Then we find out the ZC equals to negative 26.54, which is the transfer function for PD is s plus 26.54. Then we multiply back the initial transfer function. Then we will get the PID transfer function. Then after that, we find the KP, KI, and KD using the formula. Then we found that KP equals to 3367.5, KI is 1327, and KD is equals to 50. Then G is to prove from the Simulink. Then at MATLAB, then this is the result. Compare to the calculation. Then G the PID controller for system 3, and this is the transfer response. Then this is the phase margin and gain margin for system 3. which is the gain margin is infinity and the phase margin is 91.6 degree. Okay, that's all for me. Thank you.